blows up at the origin. So there's no equation of the form x inverse equals a linear combination of sines and cosines. So what's going on is that we haven't used all our assumptions about A. We assume that A has bounded condition number. So that means, and specifically we assume, let's say that A's largest eigenvalue is 1 and its smallest eigenvalue is 1 over kappa. And these x's that I'm talking about, they're just what you get from when you diagonalize both sides of the first equation. And so x essentially represents an eigenvalue of A. So all we really need is for this representation, like the x inverse equals linear combination, we just need this identity to hold when x is between these assumed values of 1 over kappa and 1, or minus 1 and minus 1 over kappa. Both signs are fine. So we just need an equation of the form x inverse equals this linear combination. It should only work on this domain d sub k that I've defined. We don't really care what happens outside of that. So if you have an equation like this with a scalar x that works on this domain, then if you plug in a matrix A over there, it'll hold for all matrices A whose eigenvalues are in this range. So that's the connection we're using here. But we've reduced the problem simply to scalars. We just need to worry about scalars. We only need to worry about approximating this function 1 over x as a Fourier series on this domain. OK, so how do we do that? So let me just restate the problem on the next slide. How do you do that? How do we come up with a Fourier series representation of this function that only needs to work on this domain? So I wasn't very familiar with the theory of Fourier series, and I'm not sure if mathematicians study this kind of stuff where you only define a function piecewise. You only define a part of the function, or like on the domain, and you say like wherever I haven't defined the function, it can just be whatever you want it to be. So there might be like a rich theory of Fourier series around this. I don't know. So, but the approach that we took was we said we'll complete the function. Like we'll come up with a function that's defined everywhere, but it's also reasonable. It's not the function 1 over x that blows up to infinity. And our strategy for making this function reasonable was, like, what was the problem with the function? The problem was that it blows up at the origin, right? So let's just multiply this with another function that doesn't blow up at the origin and is 0 at the origin, but is 1 on this domain. So when you multiply with this function, it doesn't, on the domain we have stayed the same, but at the origin now we're reasonable. So for example, let's just multiply it with the function 1 minus x squared to the 100. Okay, like 100 is just random. But what this function, the properties of this function are it's 0 at the origin, and it's 1 on our domain if you choose this number 100 to be large enough. So for some value of 100, this function has the properties we want. So if you multiply this with 1 over x, you get this function 1 minus x squared to the 100 divided by x, both of which are depicted in this diagram. So the purple function is 1 over x from before. The blue function is our new function. And as you can see, after a while, it really matches the purple function. So it's pretty much the same once you get away from the origin. At the origin, it's very well behaved because it's 0. And as you see, it doesn't go to infinity anywhere. It's like a completely reasonable function. And well, now you can apply, now you can hope for this function to have, expansions, Fourier expansions, and so forth. We've made it reasonable, basically. And so then you have to go through, well, a lot of math. And well, anyway, so I'm going to say after a lot of math, you get the final statement, which is the following. OK, I don't want you to read this theorem, but I just wanted to say that basically what we do is just read the big equation displayed up there, which is just that there's some function h of x, which we describe as a double sum over some things. Just the last term is important. The last term says it's e to the minus ix times something. That something is the t. So it's some sum over some variables. And we've expressed this function h of x as a linear combination of e to the minus ixt's. And the last line of the lemma says h of x is epsilon close to 1 over x on the domain we care about. So this is the lemma we show in our paper. It's lemma 11 in our paper. And as I said before, once you have this kind of representation, you take the linear combination of Unitary's lemma that was explained 2 slides ago, combine these 2 things, and now you have an algorithm. You still have to compute the costs and so forth of the algorithm, but the costs turn out to be what I claimed. I'm not going to do the cost analysis here. So this is the idea for the Fourier approach. The idea for the Chebyshev approach is very similar. The problem is exactly the same. We're trying to express this A inverse as a linear combination of this form, sum over n, alpha n, t sub n, a over d. T sub n is, again, the nth Chebyshev polynomial. As before, you can just think about the scalar version of this problem, which is, can you express 1 over x as a linear combination of Chebyshev polynomials? You have the same problem as before. Chebyshev polynomials are very reasonable functions. They're bounded between -1 and +1. But x inverse is a function that's completely unreasonable, close to infinity. You do the same trick. You multiply with some function. And I'm showing you the same picture again. That we'll just multiply it with 1 minus x squared over to the power 100 divided by x. That function over there is reasonable, has all the properties we want. It equals 1 over x roughly on the domain we care about. And now all you need to do is express this function as a linear combination of Chebyshev polynomials, which is actually very easy to do because the Chebyshev polynomials form a basis for polynomials. And this function over here really is a polynomial. I mean, there's an x in the denominator, but if you expand the numerator, you'll see there's x terms there. I mean, they'll cancel out, and it'll really be a polynomial. And well, at least theoretically, it's easy to express any polynomial as a linear combination of Chebyshev polynomials because they form a basis. It's not as straightforward in practice because it's kind of annoying and you have to compute these sums and so on. But it can be done, and then we do that. And similarly, we have some lemma of this form, which is just you have some function g of x. There's some coefficient over there which I want you to ignore. And finally, the 2j plus 1th Chebyshev polynomial of x. We've come up with a linear combination of Chebyshev polynomials, and the last line of the lemma says that this function, this linear combination, is indeed epsilon close to the function we care about on the domain we care about. So same thing. Now you invoke that lemma, you'll get an algorithm for solving linear equations. All right, so that brings me to the end of my talk, and let me just conclude with a summary. Thanks.
So when you simulate the Hamiltonian, don't you introduce some error?
Yes. So in fact, there's a couple of sources of error which I didn't get into, but they're all of the kind log 1 or epsilon kind of scaling error. So Hamiltonian simulation will give you an error, but to get epsilon error, you only have to pay proportional to log 1 or epsilon. So that's good, because that's exactly what we're aiming for. The approximation by the Fourier series or the Chebyshev polynomial series will also give you a little bit of error. But again, it's exactly of this kind of error, that if you go out, you only need to go out polylog 1 or epsilon terms to have the Fourier series approximate the original function to error epsilon. So we collect a couple of log 1 or epsilon terms from these sources of error, but they're all very controlled. And that's, so it works out. Yeah.
Other questions?
So it seemed when you're doing this, you multiplied the 1 over x by, you multiplied by some other function. Did you ever try, just as opposed to doing that, defining like a piecemeal function that basically connected the points?
Right. No, that's a great question. Yeah. So we had a function that was defined in some interval, and then the thing was that I didn't know how to do Fourier series with partially defined functions. And so I said, we just multiplied with some function to get a reasonable function. But what Zach's asking is, could we just have connected with some piecewise function? I guess in principle, it's fine. You could do that. But it's not clear what function you choose. Like, for example, you could just connect it with a straight line. The problem is the convergence of the Fourier series depends on the continuity of the derivatives. So if you just connect with a straight line, the first derivative is going to be bad, and it's going to be discontinuous at first or second derivative. And as soon as you get discontinuities in the derivatives, the convergence of the Fourier series is bad, and then you don't get this excellent error scaling. So what we want from the Fourier series expansion is that you only have to go out a few terms to get very close to the function. And for this, you really need, I think, that all the derivatives of the function are continuous or something. You need some kind of very strong statement on the derivatives of the function. So that approach might work, but we would need to find an amazing function to fit between them.
So generically, the kappa would be polynomial in n, right? I mean, for a random matrix of bounded norm, some model.
Yep, that's right. Yeah.
So do you
generically,
think the dependence on kappa can be improved, or is it like a hard limit?
No, the dependence on kappa is also, assuming complexity theoretic conjectures, HHL showed in the original paper. I think assuming BQP not equal to P space or BQP not equal to PP, something of that form, the dependence on kappa cannot be made sublinear in kappa. So kappa is fine, but kappa to the point 99 is not fine. So they had kappa squared, so that's exactly what the gap that Ambinus was able to close. But you cannot go below that, assuming conjectures.
If there are no more questions, let's thank our speaker again.